21, we did set up together, but admittedly there is a whole lot of steps even after that point. So, I'm okay looking at it briefly. 16, the section, the tail end section of both 16 and 21 are in, have us looking for, we're still trying to get x equals blank. There's going to be two answers, and we're going to want to use the quadratic formula. Before even plugging in any numbers, though, since our equation does not perfectly match the standard quadratic form, I would recommend we manipulate it a little bit first to get everything into the right position. Now this formula, we've done a few questions manipulating this one. This is again the formula for displacement of an object if it is based on its velocity, its acceleration, and the time in which it's able to do both of those things. Now we want, ultimately, to get to t equals blank. And since this is a complex polynomial, we've got a t squared term, and a term that has just a t, and a term that has no t at all. We're going to use our quadratic formula. We just need to get this into the correct format first. So I would rewrite this as 1/2 a t squared plus v naught t minus delta y equals 0. And once it's in this particular form, we can see that the negative delta y is going to be our c term. The v initial is going to be our v term. And 1/2 a is our a term. We do have to factor the half in, because the a term is every single thing being multiplied by whatever variable you're looking at squared. With this, now we can begin plugging things into our quadratic formula, which, refresher, is going to be, I'm going to go ahead and write t, since that's what we're looking for up here. T in this case equals negative b plus minus b squared minus 4 ac all over to a. So, before we even put in the numbers in, let's just put in the variables that we found a second ago. So our b term is going to be v naught. So negative v naught plus minus, then b squared. So that's going to be v naught squared minus 4 times a. Our a is 1/2 times acceleration. Our c term is negative delta y. Eventually, when we plug the numbers in, we will be told that delta y is already negative, so do be aware of that. That'll cancel out with this negative. And then all of that over 2 times a, and our a term is 1/2 of acceleration. Plugging our numbers into here, we'll eventually arrive at 2 answers for t, and I don't think this one should give you a complex answer, because within here we have negative of delta y, which is already negative, so those negatives cancel. A is negative, so the negative in here will cancel with this negative, meaning that everything under the square root should be positive, and there shouldn't be any complex answers. And conveniently, the 2 and the 1/2 on the bottom just cancel out. I'll leave that up here for anyone to be working with. I will accept the homework at the end of the period, so you guys can keep working on it and have it done by the end of the day. How about that? So that is 16. 21 is admittedly a doozy. What we did in class last time was rearrange the equation given in 21 to make it of the quadratic form. We start with k q1 q2 over d squared equals k q2 q3 over open parentheses r plus d close parentheses squared. We did a lot of steps to turn this and also 17 into the quadratic form. I will now put that form on the board so that we can skip the step of finding them again. We arrived at open parentheses m1 minus m3 close parentheses squared plus 2r q1 times d plus q1 r squared equals 0. And from this, you can determine m1 minus m3 is a, 2r q1 is b, and q1 times r squared is c. These are the three terms we would plug into our quadratic. The numbers involved are pretty large, so there is several algebraic steps between here and our final answer. But I'm actually going to write up the answers that I got so that you guys can compare and see that you're on the right track. The next step would be d equals negative 2rq1 plus minus 2rq1 squared minus 4 times m1 minus m3 times c, which is q1r squared, all over 2 times m1 minus m3. You could plug them in like this and then put the variables in. You could also determine what A, B, and C are and then plug them in. We can just say in our margins that we can do this math, figure out what A is equal to, and then plug that number in instead. There's a couple of different ways you can do it. The ultimate answers, I want to show you these so that you have a point of comparison. The answers that I got, which I plugged back in and did get me about the range of answers I was expecting, d equals, and they don't need to match perfectly. There's going to be some wiggle room here based on how you rounded during each step of the algebra. So if your answers don't match perfectly, that is fine. But I would be looking in the ballpark of negative 0.5998 and negative 1.435. If yours do not perfectly match, that is fine. Whatever you get, I recommend you check it back against the original. You can plug your numbers into this and see that the both sides are equal. As long as the numbers you get make this statement work, you are correct. And I'm okay if it works within a certain degree of wiggle room because of rounding. If the two sides are like maybe 2% off from one another, that's okay.
Yes. I am getting
mind sharing your answer, at least showing me? If you don't have to say it out loud, if you could just look at the paper.
I try to simplify at least one part of the quadratic, which I could, and I got this. And I even tried to graph the quadratic, but the range was too high.
That is a much bigger number than I would expect.
Under the radical, I got, like, after simplifying b squared minus 4ac, I got 8.79 times 10 to the negative 16 underneath the radical.
Right. Check. Downs. No, down. I did right down. It's supposed to be Q. Oh, sorry about that. I'm confusing my notes for 17 and 21. I apologize, everybody. I did an unfortunate there. These aren't supposed to be M's, they're supposed to be Q's. I apologize. This is what I get for mixing my notes. Terribly sorry. Okay, now the Q's. Okay. After taking the square root, this thing inside the square root, I would expect to be of the size of times 10 to the negative 16. After taking the square root.
You mean like the square root of that one number? Should be something 10 to the negative 16?
Yes.
I got 2.95 times 10 to the negative 8.
Just checking with the rest of the class real quick. Does anyone else, who else is having problems with this answer? Okay. Okay. Might waylay us on a couple of things, but let's work a few more steps in together so we can all have the same basis. One eraser is never where I want it to be. Okay, let's figure out what A, B, and C are. Trying to decide what would take the fewest steps right now. Yes, let's establish finally values for A, B, and C. A, Q1 minus Q3. Because Q3 is much, much smaller than Q1, the answer will be very close to, if not just the same as Q1, which is fine. Oh, it's not as much smaller as I thought. I was looking at the wrong number. So my A value is presently 4.315 times 10 to the negative 16th. B is going to be 2 times R times Q1. R is 0.34. So my value for B is 8.786, around there, times 10 to the negative 16th. And for C, Q1 times R squared 3.69 times 10 to the negative 16th. We'll rewrite this with the numbers plugged in. So first is negative b, so negative 8.786 e negative 16. Before we go any further, does anyone disagree with these? Okay. So use these forwards. Plus minus square root of b squared is still 8.76 e small e negative 16. Make sure that I would write this in the calculator, open parentheses, whole number, close parentheses, squared, close parentheses. Just make absolutely certain that you try to square just the 16. Then minus 4 times our A is 4.315 e negative 16. Our C is 3.96 e negative 16. Close parentheses, all over 2 times A, so 2 times 4.315 e negative 16. Anyone disagree with getting to this point? It's okay if you do, I want you to tell me. Okay. I want to simplify one line down. I'm going to recommend we figure out what b squared is, figure out what 4ac is, figure out what 2a is. So that I don't recommend doing this all in one fell swoop with your calculator, because one mistake could make the whole thing explode. So d equals negative 8.786 e negative 16 plus minus 8.786 e negative 16. Oh, I've been writing the small e's. I've been meaning to write the blocky e's. Right? Just to make it clear, these e's represent the blocky times 10 to the e, just for absolute clarity there. I'll try to start being consistent on that. So this term squared is giving me 7.719 times 10 to the negative 31st power. Please let me know if you disagree with this. Then minus, you've got 4 times 4.315 times 10 to the negative 16th times 3.96 times 10 to the negative 16th. That's going to give us positive 6.399 times 10 to the negative 31st. Anyone disagree with this? Okay. And then that's the end of the square root part. That's all over 2 times A, times 2 times 4.315 e negative 16 is going to give us 8.63 times 10 to the negative 16. The next line, I do feel comfortable trying to resolve the entire radical at once. I think we can figure out what this square root is all in one go. And we are not in danger of imaginary numbers here because the positive number is bigger than the negative number. So we're not going to have to deal with any i's. B equals so 7.719 e negative 31 minus 6.3 9, e negative 31. Do that subtraction, then take the square root. And that gives me, please tell me if we have differing answers, 3.67 times 10 to the negative 16th. Getting a couple of quizzical glances. I did separate this into two lines. I found what the difference is, and then I took the square root of it using the answer function. And then all over still 8.63 e to the negative 16. This will now give us the two differing answers. Yes. Let me refine. I can refine them real quick just so that we have all the same numbers here together. So I'd rather show you based on what we've done here today rather than what's in my notes, which could be off due to rounding differently last time. So I will find these from this statement onwards very quickly so we can all compare. Negative 8.7, 6, 8, 16. Plus 3.67 divided by answer by 8.63. So the first answer that I have gotten here today is negative 0.5928. I'll round it off there. That's our first one. Second one. Do the minus instead. I have negative 1.4433. Both of our answers are negative in this situation. That is okay. Nothing broke. Two negatives is way better than any imaginaries. I believe that is a little different. Only technical. I know that 17 and 21 are the single largest amount of big numbers in algebra you might have done up until this point. So I am happy to step through them with you. In the types of equations that these are referencing, the formulas where we were looking at the force of gravity between multiple objects or the electrical force between multiple objects, there will be similarly large numbers involved. But, at least in my experience, very rarely do we end up needing to do the quadratic with them. It does come up in edge cases, which is why we're practicing now. But this is not going to be every single physics question in the world, I promise you. There will be large numbers involved, but very rarely are we going to have to go through every single step in 1721. Occasionally, that might be like the big test question, but not always. And large, either very, very large numbers like in the gravity formula, or very, very small numbers like in these electrical formulas are going to come up a lot when you're looking at things on those types of scales. Planets have very large masses, meanwhile charged particles have very small amounts of charge. And so what we've ultimately found here is how far apart the particles in this question are. In order for the forces on these three particles to be balanced, we've solved for the distance between them, where they would have to sit such that everything is in homeostasis. In 17, what we would have been solving for is how far apart these planets and moons and satellites would need to be for the gravitational forces to balance and for everything to orbit nicely. Which explains why those numbers are probably a bit larger. Oh no, I got two small numbers for that. Never mind. But the numbers in the question is any, and I do please mean any, questions at all about 21 or 17. Okay. Does anyone feel that they will need more time than by the end of the class period to finish this assignment? And the sooner I get it, the sooner I can grade it. So if I can get it all, if I can have everyone's answers by the end of the day, I'll have them graded and back to you by Friday. So again, if you're still finalizing things, have it up here by the end of the period, that is more than fine. You put it in, you can put it up here on your way out. Additionally, I have for you the fourth assignment, and last week I put up a fourth assignment onto the Brightspace page. If you've been looking at that, I have now changed it rather significantly. I've looked at where we were in the course, what things I wanted to cover, and I have overhauled this particular assignment. So this is the new version, and I will be uploading this file to Brightspace as well. I'm going to be uploading the assignments in general from now on. If you'd rather work from a digital copy and not need to collect and turn in a physical piece of paper, then the files will be up there for you to use. But if you want the paper, I'm old-fashioned. I do prefer writing things down. But you don't have to. You can use a digital one if you have a means of looking at it and submitting your answers. You can write them on a different sheet, or you can even put them in the file if you have. I know a lot of students these days are using tablets where you just write on the document. I will accept those types of files as your submissions. If you want paper copies, they are up here. And this particular assignment has 3 pages, but that's because each of the individual questions takes up an amount of space, because we're going to be looking at triangles and unit circles, which, though tedious at times, forms the backbone of a lot of intro-level physics, because as a physics professional, I can turn most things into a triangle. You will never escape geometry. This is true of physical triangles, like when you're measuring the distance between 3 points, or when you're trying to figure out the hypotenuse of a system. This is also true of slightly more esoteric triangles, because anything that is a vector, distance, velocity, force, you can make into a triangle. There are triangles made of force that you can't see except when they push things in a direction. So it's important for us to review these principles so that you will be acclimated to them in future classes. Now, in a previous life, I taught high school physics, and I heard a lot of my students complaining about their geometry and trigonometry classes. And I was always a little confused at first when they started complaining, because at least for me, trig and geo were usually pretty fun. Playing with shape, doing trig functions, that just appeals to my brain. I know it doesn't appeal to everybody, but it didn't seem like the worst thing in the world, like they were making it sound like. I asked them what they were doing in their classes, and they were describing things like proofs and integrals and derivations, which to me is not trig or geo at all. At least not, maybe they've changed the labels of a few of the classes after I came through high school. So I want to assure you what I mean when I say trig and geo. We are looking at triangles and unit circles. We're not doing proofs. If you had to do a trig or geo class with proofs in it, you're safe here. This is just algebra based. There's no need to panic. I kind of can't believe that they put those things into those types of classes. I don't know why they changed the labels after I was out of high school. We are going to be using just trig and geo and Pythagorean theorem and similar concepts to examine the types of pretty much every triangle that's going to come up here is going to be a right triangle. So this assignment is just going to be review of measuring all the sides, figuring out the sides you don't know, figuring out the angles you don't know. And a couple cases of how we would apply this to physics. Does Does anyone want me to not erase 16? Okay. So, behold the right triangle. It's called so because it has a right 90-degree angle in it. Every single triangle on the assignment 4 is a right triangle. There's no need to worry about there being weird scaling or isosceles present. Because it's a right triangle, there are very specific rules that apply to all of these triangles. And the reason that these come up a lot in physics is because when we are looking at 2-dimensional and even 3-dimensional motion or vectors, the 3 axes that we tend to examine are perpendicular to one another. We live in a 3-dimensional universe, at least in terms of the physical space that we inhabit, meaning that from point A to point B, you can define the differences in terms of horizontal x, vertical y, and the depth or z-axis. All 3 of those axes are perpendicular to one another, meaning they form right angles with one another. So any single problem involving this type of axis or graph is likely going to have some right triangles in it, which is why we're studying them. So, as for how this could be specifically applied, the very first question on the assignment is going to have us estimating something in the real world based on triangles. So, the classic example, you have some object of some unknown height, because good luck putting a tape measure up to the top of a tree. You can try. Knowing my luck, it would definitely fall over. The tape measure, maybe the tree. Not entirely sure how tall this particular tree is, but there are some things we can more easily measure with a tape measurer. For example, I'm going to call this the A length. We could measure some distance along the ground. Now, a common application of this is if you measure, say, the length of the tree's shadow, that shadow is being cast by the light of the sun. Stick with me for just a second. We can measure how long the shadow is. That would be this side of the triangle. And with a protractor and sunglasses, you can figure out the angle between the end of the shadow and the sun. So on this grand right triangle that we have constructed overtopping the real world, we have one triangle leg and really 2 angles, because we know, we're assuming, the flat ground is perpendicular to the vertical height of the tree. So that gives us 1 leg and 2 angles, one of which is a right angle, which tells us all of our Trig and Geo and Pythagorean stuff will work here. So, just starting cold, if we can use a tape measure to measure the length of the shadow, and we can use a protractor to figure out the angle of the sun, how can we approximate the height of the tree with just those pieces of information? Okay, this is the cold open.
When you plug it into the... Can you repeat the question?
Sorry, 2 people were speaking at once. One at a time, sorry. Yes.
Can you repeat the question?
Oh, if we know the length of the shadow, and we know this angle, and we know that this is a right angle, how can we find, I'll label it as B, the height of the tree? All right, you raised your hand next.
Oh, yeah.
You were speaking up.
Couldn't we plug it into like the equation?
Okay, we have equations that we can use. We're going to review them briefly today.
Well, I have 2 questions. So is the triangle representing like the angles and stuff, like the triangle starting off.
It's okay.
Is that representing the height of the tree?
So B on this triangle represents tree height.
Okay,
A is shadow length.
okay.
So if I were to redraw this, because I know overlapping the triangle sometimes causes things to superimpose onto each other in weird ways. Tree height, shadow length. And then this line would continue on to the side.
Okay. Well, then can you just use like second row?
Very good. So, first thing we're going to review is everyone's favorite mathematical thing to scream at one another, SOHCAHTOA. Has anyone not heard that acronym before? Okay, that is fine. That's why I'm going to write it. So, Kach, and Toa. This mnemonic, a very interesting thing to say repeatedly, reminds us what goes where in the common trig functions. If you look at your calculator, which you're contractually obligated to refer to at least once per day, you will see that we have on the front plate sine, cosine, and tangent buttons. These are our trigonometric functions. And when you plug things into these functions, it will give you some information about the triangle that those things came from. If you push the sine button, it loads up SIN. I'm going to call it sine because SIN is short for a full word, SINE. So sine of something. It opens up a parentheses. You have to put something in that parentheses, and it will then perform the sine operator upon that number. Like how if you square something, it performs the squared operator on it. And this mnemonic is to help remind us what goes into which trig function. I know the class period is ending, so I at least want to get this on the board with everyone's notes before I set you loose. So the mnemonic tells us that sine of anything will be equal to the opposite leg over the hypotenuse. And if this was our sample triangle, who and why? I don't know. If this was our sample triangle, we need to start from an angle. This is the angle we know that isn't a right angle. You can't start from a right angle. It has to be one of the other two. So if this is the angle we're beginning from, I put the Greek letter theta in here, which is just mathematical shorthand for an angle usually. This is our theta. This is our known angle. Because we know in this situation we measured the angle between here and the sun. We know this angle, and we know one leg of the triangle. To label what each of these legs are in relation to that angle, let's start with the one that's always going to be the same on every triangle. The slanted leg is always the hypotenuse on a right triangle. So that's always going to be constant. If we were looking at the Pythagorean theorem, that would be C, the hypotenuse. On this particular triangle, we don't know the hypotenuse yet. We do know A. And in relationship to this angle, A is the adjacent leg, because it is physically touching the angle that we are looking at. It's the one touching the angle that isn't the hypotenuse. Hypotenuse always has its own unique title. The other leg, since this B leg is not touching this angle at all, is our opposite leg. So we know this angle. If we were to perform the sine operator on this angle, if it was say 15 degrees, and you put sine of 15 degrees into your calculator, it would give you some number. So sine of 15, if I just put that in, it gives me some number, about 0.26. What that means is, whatever that calculator just gave me for sine of the angle is equal to the length of the opposite leg divided by the length of the hypotenuse. So if we did plug in sine of, say, 15 degrees, we got 0.26. That 0.26 would be the opposite over the hypotenuse. If you knew either of these, you could use this statement to find the other one. Now, does that help us find the tree height in this specific situation? No, because the tree height is our opposite. Okay, well, tree height is our opposite leg. That is what we want. But we arrive at the statement 0.26 equals opposite over hypotenuse. We don't know the hypotenuse. So let's briefly look at the other ones so that they can be in your notebook. Next, the calf part. We have cosine. This marker's running out of ink. Forgive the color swap. Cosine equals adjacent over hypotenuse, which would look like this. So if you use the cosine operator instead, the number you get would be the length of the adjacent leg divided by the hypotenuse. Will this tell us the height of the tree in this situation? Also no, because the height of the tree is the opposite leg. The opposite variable is not present in this one. That leaves us with one more. TOA stands for tangent function. Tangent theta is equal to opposite leg over adjacent leg, which would look like this. Tangent theta equals op over adjacent. TOA, yes, that's right. If we know theta and the adjacent leg, which for the sample written over there would be shadow length and the angle between the shadow and the sun, we could use this to solve for tree height. So, make sure you have these in your notes. These are the three operators that most of you should be exposed to by now. Friday, as we look further at the assignment, we will talk about, we'll look at specific triangles, and we will talk about the three other operators and how they relate back to these first three. So, if you want a paper copy, please do come up and collect one, and make sure your homework is in, homework 3 is in the back. I'll have those graded for you on Friday. If you have any questions at any time while we're doing the assignments, please do email me.